Today we shall discuss order of an element mod P. P is a prime number and A is an integer. We know that A raised to phi m is congruent to 1 mod m if A and m, they are co-prime. GCD of A and m is 1. So first we will study order mod n, and then we will see in particular what happens if m is a prime number. So this power phi is the Euler's function. This power of A is 1 provided A and m are co-prime. You can take the smallest positive integer, let us say k, such that A raised to k is congruent to 1 mod m, and such a k is called order of A mod m. So if k is the least positive integer, such that A raised to k congruent to 1 mod m, then k is called as the order of A mod m. Then k is called the order of A mod m. The other way of saying this is that A belongs to the exponent k modulo m. A belongs to the exponent k modulo m. This way of saying is old terminology. A belongs to the exponent k mod m. But nowadays, as in group theory, we have the concept of order of an element in a group. Similarly here we have order of A modulo m. So because of Euler's theorem, A raised to phi m is 1 mod m when A is co-prime to m. So there is always this least positive integer. So every A such that A is co-prime to m will have some order which is a positive integer. Here the condition am equal to 1 is necessary. Because if A is not co-prime to m, then there is no possibility of any power of A being congruent to 1 mod m. Okay. So note this fact that if am equal to d bigger than 1, then for no k bigger or equal 1, A raised to k can be congruent to 1 mod m. That is because if it is so, see that for if A raised to k minus 1 is a multiple of m, say t times m, then what happens? D GCD divides A, D it divides M also, so D will divide 1, that's a contradiction. Then since D divides A and D divides M, we get D divides 1, and this is a contradiction. Okay, D divides these two, so D has to divide 1. That means this concept of order of an element mod M, that will be there provided A and M, they are co-prime. That is a necessary condition. Then we will study some properties of order. So, lemma let AM equal to 1, so if, let us say, order of, so we denote it by order of A mod M is H, then for any n such that A raised to n congruent to 1 mod M. Suppose n is a positive integer such that A raised to n is congruent to 1 mod M, we must have that H divides n. So the set of all powers of A which are 1, they are just multiples of H. Now this is an easy consequence of the division algorithm. Proof, right? N equal to H times Q plus R, where Q is the quotient and R is the remainder. Zero less than equal to R less than equal to H. So divide N by H, get the quotient, get the remainder. Now N is a positive integer, we can take N to be, we can say any N bigger equal 1, such that A raised to N congruent to 1 mod N, H must divide N. So A raised to N equal to A raised to H raised to Q into A raised to R. Now A raised to N is given to be congruent to 1 mod M. A raised to H, H is the order of A, and therefore A raised to H is also 1. And that means that A raised to R should be congruent to 1 mod M. Therefore A raised to R congruent to 1 mod M. Now if 0 less than R less than H, then we get a positive integer r less than h such that a raised to r congruent to 1 mod m. That's a contradiction because h is the order of a mod m. H is the least such that a raised to h congruent to 1 mod m. So this contradicts that h is the order of a mod m. H least with this property that a raised to h congruent to 1 mod m, h is least. No smaller positive integer can have that property. And this means that r must be 0. Therefore, r is equal to 0. And r is 0 means h divides n. Therefore, h divides n. You can think of negative integers n for which a raised to n congruent to 1 mod m, and such negative integers you can easily see that they also have this property that h divides n. What's the negative power of a? A raised to minus 5, for example. It means a inverse raised to 5. You can understand it that way. What is the order of a inverse? Order of a inverse is the same as order of a. So note, if a has order let us say h and a bar is such that this order is mod n, order of h mod n, and a bar is such that a bar congruent to 1 mod m, then order of a equal to order of a bar. This order is, here we are considering order mod m. Order means order mod m. See that these are positive integers. Orders are positive integers, and one way to show that two positive integers are equal is one divides the other. First number divides second, second divides first. That is one usual way of so proof of this, let order of a mod m be h1 and order of a bar mod m be h2. Now a raised to h1 congruent to 1 mod m. Multiply both sides by a bar raised to h1. What do you get? A bar raised to h1. On the left hand side you get a bar raised to h1 congruent to a bar raised to h1 mod m. What is a bar? It is 1 mod m. Therefore, a bar raised to h1 is congruent to 1 mod m. Now, this is a power of the element a bar, which is 1. Order of a bar is assumed to be h2. Therefore, this order has to divide this number h1. Since order of a bar mod m is h2, h2 divides h1. And in a similar way you can prove h1 divides h2. Okay. Similarly, h1 divides h2. Because you start with a bar raised to h2 equal to 1. A bar raised to h2 congruent to 1 mod m, and then multiply both sides by a raised to h2. Here also it will get a raised to h2. Now a bar raised to h2 is 1, and a raised to h2 is 1 mod m means order of a must divide h2, that is h1 divides h2. So similarly you are getting h1 divides h2, and therefore h1 equal to h2 since both are positive integers. We have two positive integers such that each divides the other, then they are equal. So order of an element and order of its inverse, they are same. Let us take an example. Take m equal to 10 and take an element which is coprime to 10. So let us say 3. What is the order of 3 mod 10? So 3 raised to 1 is 3, 3 raised to 2 is 9, none of this is 1 mod 10, 3 raised to 3 is 27, that is congruent to 7 mod 10, 3 raised to 4, that is congruent to 7 into 3, 21, that is congruent to 1 mod 10. So here 4 is the least such that 3 raised to 4 is congruent to 1 mod 10. So order of 3 mod 10 is 4. Here order mod 10, you should understand that it is not that we find out some order and that is some number, then you reduce that number mod 10. It's not like that. Here you are considering, essentially you are considering residue classes mod 10. So 3 is an element, its residue class. 3 mod 10. 3 mod 10 means the residue class of 3. Any number congruent to 3 mod 10 if you consider, its order is going to be this number. So if I consider say 13 instead of 3, that positive integer, it belongs to the same residue class. What is its order? It is same as the order of 3. 3 and 13 belong to the same residue class mod 10. So these are orders of elements, but these are actually orders of residue classes. That is to be understood here. Essentially we are considering the group of integers, we can say less than equal to m and relatively prime to m. This group is with respect to multiplication mod m. So reduced residue system mod m, that actually forms a group, and in that group what is the order of an element? That's what is being considered. So in this case, what is phi of 10? Phi of 10 is 4, and this is an element of order 4. So here phi of 10 equal to 4. So this element is of maximum possible order, and such an element 3 has maximum possible order. And such an element which has maximum possible order is called a primitive root. See, note that a raised to phi m is always 1 when a is coprime to m. So order can never exceed phi of m. There may be some elements which attain this order, and these are called primitive roots. Such an element is called a primitive root for the given modulus. For the modulus 10. In general, you can think of m, and an element of order phi m will be called as a primitive root mod m, provided such an element exists. If I take the element 9 here, what is its order? 9 square is 81. 81 is 1 mod 10. So order of 9 is just 2. Okay? So different elements can have different orders, and those elements which attain the maximum possible order, they are called primitive roots. Now, or we can do this as a further proposition. If order of an element is known, what is the order of some power of this element? So, in this example, you see that order of 3 is 4, and 3 square is 9, and order of this power square comes out to be half of this order, 4 by 2. You are raising 3 to second power. So that kind of result is true. If you take a power such that here 3 square, 2 divides 4, then the order of 3 square is half. So if something of this type is true, you can get order easily. But sometimes you are considering a raised to k, and k does not divide the order of the element a. Then you cannot say that order of a raised to k is order of a divided by k. That kind of thing is not true. So what is the result? So suppose a equal to 1, and order of a mod m is h. Then order of a power a raised to k mod m is h divided by the GCD of h and k. H divided by the GCD. So divide the order of A by the GCD. In particular, suppose this K divides H. In particular, if K divides H, then the GCD of H and K will be K only. K, and the order of A raised to K will be H by K, and of A raised to K mod M is H by K. So proof of this, usually when you have GCD of two numbers, it is convenient to write the GCD as a combination of the given numbers, and that can be used. So here HK equal to R, say, so A raised to K okay, so maybe let us try this. Write H is equal to H1 into R, K equal to K1 into R. So what is A raised to K raised to H1? This is A raised to K means K1 times R raised to H1, which is A raised to RH1 raised to K1, but RH1 is H, A raised to H is congruent to 1 mod M, therefore this power is congruent to 1 mod M. So we have shown that A raised to K raised to H1 is congruent to 1 mod M, and therefore order of A raised to K divides H1. Order of A raised to K mod M divides H1. Now we should also use that order of A is given to be H. Suppose some power a raised to k raised to n is congruent to 1 mod m. Some power is 1. Therefore, a raised to kn is 1 mod m. That's what we get. And what is the order of A? Order of A is H. That H has to divide k times n because H is the order. Therefore, H divides kn since order of A is H. Order of A mod m is H. So H divides Kn. Now you can divide both sides by R. Therefore H by R divides K by R times N. Because R is the GCD of H and K, R divides both H and K. What is H by R? That is H1. H1 divides K1 times N. What can we say about H1 and K1? See, R is the GCD of H and K. H1 and K1, they don't have anything common. The GCD of H1 and K1 is 1. But H1, K1 GCD is 1. Therefore, H1 has to divide N. H1 divides Kn, H1 K1 equal to 1. Therefore, H1 divides N. So, whenever any power is there of a raised to k and that power is congruent to 1 mod n, that power is divisible by h1. Okay, and that shows already a raised to k raised to h1 is 1 mod n. Any power like this, a raised to k raised to n, that suppose you assume to be equal to 1, then that is divisible by h1. That means what is the smallest number with this property? It must be h1. Therefore, so these two things we are using. Therefore, the smallest number t such that smallest positive integer t such that a raised to k raised to t congruent to 1 mod m is h1. Okay. First of all, we have shown that a raised to k raised to h1 is 1 mod m. Second thing is, any t if you are given such that this is 1, then t is divisible by h1. So these two things will tell you that the smallest one is h1, and that means order of a raised to k is h1. Therefore, order of a raised to k mod m, order of this residue class is h1, that is H1 is H by R, that is, what is R? R is HK, H by HK. So if you know order of A, you can find out the order of A raised to K easily by using this result. What is the order of product? Suppose you know order of A and order of B. Can you say something about the order of the product A and B? In general, we cannot say anything, but if the orders are coprime, then we can say that the order of the product is equal to the product of orders. You cannot say that order of AB equal to LCM of orders. That kind of thing is not correct. A simple example is, suppose you take A of some order. So order of A mod M, this is equal to H say. Suppose A bar is the inverse of A mod M. Inverse of A mod M, that is A bar congruent to 1 mod M. Then what is the order of A bar? It's also H. A bar mod M is H, same order. Now, what is the LCM of these two orders? It is H. Is the order of A bar equal to H? No, because A bar is 1. Modulo M, A bar is 1. And what is the order of 1? It is 1. So, but order of A bar is not the LCM of H and H, that is H. Not LCM, I wanted to say GCD of H and H, greatest common. Product of orders, product means LCM. But of H and H, that is H. It's not H, because it is just 1, as A bar is congruent to 1 mod M, and order of one mod M is just 1. So if you take orders as coprime, then if you take the product of the two elements, then order of the product will be equal to the product of the orders. So this is the next theorem. Let's suppose order of A mod M is H and order of B mod M is K. Then order of AB mod M is H times K. It is the product of the orders. For example, if you have an element of order 2, another element is of order 3, then the product will be of order 6. Okay. This thing you can think of in group theory also, but there you have to be somewhat careful. The group should be abelian. Okay. Like S3. In the group S3, take an element of order 2 and an element of order 3. The product will not be an element of order 6. There is no element in S3 of order 6. Okay. So this is such a property is true for commutative groups. So proof. So first, if you take AB raised to HK, that is A raised to HK into B raised to HK, which can be considered as A raised to H raised to K into B raised to K raised to H. But A raised to H is congruent to 1 mod M and B raised to K is congruent to 1 mod M because H and K are orders. So this is congruent to 1 mod M. Since A raised to H congruent to 1 mod M and similarly B raised to K, both are congruent to 1 mod M. That means order of AB divides HK. Yeah, here I had to write HK is 1, that I didn't write, and HK is 1. That's important. Then the order of AB is equal to the product of the orders. Okay. So if the order of AB is R, AB mod M is R, then what have we shown so far? R divides HK. R divides HK. We have to show HK divides R, and for that you have to show H divides R and K also divides R. So consider A raised to R times K. This is congruent to a raised to rk into b raised to rk mod m, since b raised to k congruent to 1 mod m. So b raised to rk, that is b raised to k raised to r, so that is 1. But this is congruent to ab raised to rk. Power is same. This you can write as ab raised to r raised to k. But what is ab raised to r? We are assuming that r is the order of ab mod m. R is the order of ab mod m. Therefore ab raised to r is 1 mod m. So this is congruent to 1 mod m. What does this show? This shows that order of A has to divide Rk. Therefore, order of A mod m divides Rk. A raised to Rk is 1 mod m. So order of A mod m divides Hk, H divides Rk, Hk equal to 1, H divides R. In a similar manner, you can show that K divides R, because you can start with B raised to RH and do the same similar calculation. So similarly, K divides R. But H and K are co-prime. Again, H divides R, K divides R, therefore their product must divide R. Therefore HK divides R. So earlier we have shown that R divides HK. Thus R divides HK and HK divides R. So R equal to HK. That is, order of AB mod M is equal to the product of the orders. Order of A mod M multiplied by order of B mod M. This happens when the orders are co-prime. So far we have seen that order of any element, any integer mod m, it divides phi of m. Sometimes there are elements whose order is the maximum possible order, phi of m, and such elements are called primitive roots. order of product is equal to product of the orders provided the orders are co-prime. Let me take another example to show that primitive root may not exist. So take m equal to 8. What is phi of m? 4. If you take the elements in the reduced residue system, that is the elements which are co-prime to m, so the reduced residue system mod 8 is this set 1, 3, 5, 7. This is standard reduced residue system. That is, you consider numbers from 0 to 7 and find out which of them are co-prime to 8. So 1, 3, 5, 7 are co-prime to 8. This is the standard reduced residue system mod 8. What are the orders of these elements? So orders, let us list the orders. This is order 1, 3 square is 1, so order is 2, 5 square is 1 mod 8, order is 2, and this is also of order 2. So there is no element of order 4, which is phi of 8. So no element of order 4. That is no primitive root. Mod 8. There is no primitive root, whereas for 10 there was primitive root. If m equal to p prime, what is phi of m? That is p minus 1. M is prime, phi of m is p minus 1. And in such a case, there will always be a primitive root. There will always be an element of order p minus 1. So let us take an example. Take p equal to 11. Try to get some element whose order is 10. So let us try a equal to 2. If this is of order 10, that's fine. Otherwise we will try with next one. Let us see. 2 raised to 1 is 2. 2 raised to 2 is 4. 2 raised to 3 is 8. 2 raised to 4 is 16, that is 5 mod 10. So congruent to 5 mod 11. 2 raised to 5, that is congruent to 10. We can say it is congruent to minus 1 mod 11. Still we have not got 1 anytime. If I go to the next power, 2 raised to 6, this is minus 1 times 2, so it is negative of this, minus 2, that is also not 1. So if you make a table of higher powers, 2 raised to 6 will be minus of 2, and minus 4, minus 8, minus 5 and plus 1. So going ahead you will get 2 raised to 10 is congruent to 1 mod 11, and 10 is the least with this property. Okay. So order of 2 mod 11 is 10, that is phi of 11. This is an example where 2 works as a primitive root. 2 is an element of order p minus 1. 2 is called a primitive root. Mod 11, because its order is the maximum possible. Two may not always be a primitive root. For example, if I take p equal to 7, what is phi of p? P minus 1, that is 6. What are the possible orders of 2? Can you tell me possible orders of 2? Order of 2 has to divide this number. Always. Order of an element divides phi of m. So it is either 1 or 2 or 3 or 6. These are the 4 possibilities. And you will just see that 2 raised to 3 is 8 congruent to 1 mod 7. So 2 is not a primitive root. Mod 7. But something else can be. So take the number 3. So what is 3 square? It is 9. 3 cube is 27. And this is congruent to minus 1 mod 7. See that you don't have to calculate higher powers. 3 is not 1, 3 square is not 1, 3 cube is not 1, so order is neither 1 nor 2 nor 3, so it has to be 6. Because the only possibilities are 1, 2, 3 and 6. So order of 3 mod 7 is 6, and 3 is a primitive root mod 7. We will see that for any prime, primitive root exists. So I will now define what's a primitive root. Let m bigger equal 1. If there is an integer a such that a raised to pi m, so if you can say in short, if order of a mod m is phi of m, then a is called a primitive root mod m. And what are the values of m for which primitive root exists? These values are taken together in this theorem. So primitive roots exist for m equal to p raised to r, 2p raised to r, 1, 2, 4, where p is an odd prime and r bigger equal 1. These are the values of m for which primitive root exists. Powers of an odd prime, 2 times power of an odd prime, and powers of 2 only 2 and 4. 8 does not have a primitive root.